Hi, I'm Kyle. I'm a second year undergraduate at Georgia Tech, and this is the second part in a series that I'm doing where I'm going from zero to the conservation of energy using classical mechanics. In the first video, I derived the Euler-Lagrange equation, which states that the partial derivative of a Lagrangian with respect to position minus the total time derivative of the partial derivative of the Lagrangian with respect to velocity equals 0. In this video, I wanted to talk about Galileo's relativity principle, but before I get to that, I wanted to talk about the principle of least action just a little bit more. For those who don't know, the principle of least action takes the form of S equals the integral from t0 to t1 of some function that we call the Lagrangian that depends on position, which is q, the time derivative of position, which is velocity, and time itself with respect to time. And using the calculus of variations, we took this principle of least action and derived these Euler-Lagrange equations up here. So imagine I have another Lagrangian called L prime in addition to this L here. And we'll say that this L prime depends on L, but it differs by a total time derivative of a function, which is arbitrary, of position and time. Okay, now let's look at what happens when we apply the principle of least action for this new Lagrangian. So we'll say S prime, which is the new action, is going to be equal to the integral from t0 to t1 of this new Lagrangian, position, velocity, time, respect to time. And what we'll notice is we can actually look at what this L prime is made of. And we can express this alternatively as the integral from t0 to t1 of L, the normal L, of q, velocity and time with respect to time. Sorry, this should be an equal sign. Plus the integral for this term, which will be from t0 to t1. Oops, t1 of d over dt of f of q, oops, that's g, q, t, dt. Okay, great. Already getting long-winded. So we can do something kind of interesting here. If we remember the fundamental theorem of calculus, which I'll just restate up here, that is, if we have the integral of a to b of some function of x dx, saying this is the same as f of b minus f of a if the derivative of f with respect to x is f of x. Okay, so notice how we can apply this down here. Pretty much, because this is already like wrapped in a derivative, we can kind of just pull it out of that. And what we end up getting is we have some term of f of q at t1 and t1 minus f of q at t0, t0. Okay, and remember q is going to change with time. And if you read Landau, he'll have an alternative notation for this, but it means the same thing. We're talking about the position of our particles at t1 versus the position of our particles at t0. Okay, and I'll drag this guy back down here. What you'll notice here is my action is effectively just changing by some constant, right? So we're evaluating this function f, which is still arbitrary, at the boundary conditions. So where the positions start, where the particles start and where they end, and when time starts and when time ends. It doesn't, there's no integral here. We're effectively just adding some constant. Okay? Now, if you watch the first video, we talked about how if you were to plot the action, S prime, against epsilon, and epsilon comes from when we start doing variational calculus. And again, watch the first video if you're not familiar with that. We get something kind of like this, where we have a minimum right here where epsilon equals 0. And we go on to use this to derive the Euler-Lagrange equations. But now that we're shifting this S prime by some constant, we'll have something kind of like this. Okay? And now what's interesting is when we actually start going through the calculus of variations, a constant shift of the Lagrangian will just fall off when we start doing variational calculus. So again, if you watch the first video, you'll know that we take the derivative with respect to epsilon after changing the definition of q. And because our change q, again, you'll have to watch the first video to understand this, because our change q is going to have the same endpoints, it's not changing at all with epsilon. So when we take the derivative with respect to epsilon, this constant bit just is a constant and it disappears. So the moral of the story is if we shift the Lagrangian by some constant, the Euler-Lagrange equation is not going to change. It's still going to apply. And because the Euler-Lagrange equation dictates the laws of motion, or I should say the equations of motion in two Lagrangians that differ only by a total time derivative are going to be exactly the same. So I'll express this again. This is pretty important, and we'll see why this works. Okay, so if a Lagrangian L and another Lagrangian L prime differ only by a total time derivative, then their equations of motion are exactly equal. Okay, and this will tie into Galileo's relativity principle, which is talking about when we can treat the equations of motion in different frames as equal. And also as a side note, if you're curious about the different forms that this function f can take, because it can have some different parameters, I'm going to link a physics stack exchange discussion in the description of this video if you're curious, because it is kind of interesting. Okay, so now let's finally move on to the big topic of this video, Galileo's relativity principle. So Galileo's relativity principle says that a system's equations of motion are the same in all inertial frames. So let's unpack this by first discussing what an inertial frame actually is. An inertial frame is usually described as one that isn't accelerating, and this is usually good enough for most applicable physics, but the definition is weak in nature. Acceleration, as we know, is the second time derivative of position, and our position is always measured relative to something else. And if that something else is moving around and accelerating, we might inadvertently, label ourselves as in an inertial frame if we're accelerating with our reference point. So, we need a better definition of what actually constitutes an inertial frame. So the way we, get a better definition is we have these three rules. So we say, if the following are true, then we're in an inertial frame. And the first condition is that space is homogeneous. I'll get to what that means. Secondly, we say that space is isotropic. And third, we say time is homogeneous. So first, let's define these terms. Homogeneous means that something consists of parts made of the same kind. And in the context of space and time, we're saying that all positions in space are equal, and similarly, all instants of time are equal. Now, what does this all mean in the context of classical mechanics? If the equations of motion in our reference frame are changing depending on where our frame is, then we're violating this first clause here. And similarly, if the equations of motion in our frame change depending on when we do our experiment, we're violating this clause here. And as for the second clause, if the equations of motion in our reference frame are changing depending on how our frame is oriented, we're violating this second clause. Okay? Now, this is a lot to unpack. So let's imagine some scenarios where we might break some of these rules. So if my reference frame is on a spinning disk, like a merry-go-round, I'll notice that, first of all, the equations of motion change depending on where my frame sits on the disk. The centrifugal force will be different if I'm close to the center, if I'm on the center, or if I'm out here. Because the equations of motion depend on where my frame is, this is a violation of this first clause up here, that space has to be homogeneous. Secondly, if I took my frame and I rotated it 90 degrees, all of a sudden all the centrifugal acceleration is going to be going in a different direction. And this is going to be violating that second clause that says that space shouldn't have a bias in a certain direction. And you might be thinking about okay, what about gravity? And I'll get into that a little bit. And now let's think about time. This is a little harder to visualize. Now imagine the disk's angular velocity spins twice as fast after like 3 o'clock. In that case, my equations of motion in that frame are going to have to account for that. And that's a violation of this third clause. And again, I know this is kind of hand-wavy, and I'll try to delve more into it. But these are the three main things that constitute an inertial frame. Now, if instead of defining our reference frame here, we zoomed out and we made this whole thing our reference frame, and say the ball I was studying is still here. Now, if we like neglect like the spin of Earth and little things like that, now we have an inertial frame here. And as Landau states in his mechanics book, which is what I'm going off in these videos, you can always zoom out enough to find an inertial frame for whatever system you're looking at. So while physics and like the principle of least action do work for non-inertial frames, it always makes sense, like for practical reasons, to zoom out and look at the inertial frame. Unless you're like in a centrifuge or like some like edge cases where you might want to use non-inertial frames. In the vast majority of cases, you're going to be using inertial frames just because they're so much easier to work with. Now I want to make a few comments here. Here I said that the equations of motion cannot change with time. That isn't to say that they can't depend on time, they just can't depend on like an absolute time. Now think about a spring oscillating. Say I pull it down and I start a timer. I get to choose when to start that timer. I expect the displacement to follow this exact same path every time I repeat this experiment, provided I don't like screw it up or anything. Now, if time were to lack homogeneity, I wouldn't get to arbitrarily pick when to start my stopwatch. I'd have to have some knowledge about how my reference frame depends on time. Now, imagine I was performing this spring experiment on the merry-go-round that spins twice as fast after 3 o'clock. In this scenario, I would have to know what time of day it is so I could adjust my equations of motion accordingly. When we pick an inertial frame, we're simplifying the problem so we don't have to deal with things like this. We allow the origin of time to be an arbitrary pick that simplifies our problem. I wanted to add one more comment about the isotropy of space. When I was first reading through this for the first time, I was wondering why Earth doesn't constitute a non-inertial frame. If I have a ball up here, it's gonna like fall down, right? And this looks like some bias in direction. And even furthermore, if I had a frame, actually, we'll just copy this. If this frame were in deep space, I could put like a rocket on it and accelerate it at 9.81 meters a second. And if I'm the ball or if I'm in this frame, there's nothing I can do to tell if I'm on Earth or if I'm accelerating upwards. And Einstein himself actually addressed this question when he was going through general relativity. And for now, what we're going to think about is on Earth, we're going to say that this ball is in some potential energy function, and I'll get to that later. And this one here, we'll say this just isn't an inertial frame because it is accelerating. Okay? And with relativistic mechanics and the more fancy stuff, it gets a lot more complicated. So now let's imagine what the simplest system looks like. A free particle, so like a baseball in space that doesn't have any potential energy. And like it's not going to do anything until we like push it or something. Okay? So usually our Lagrangian is a function of q dot, and t. So we can make a few simplifications for this. Firstly, because there's no potential energy, and because we're in an inertial frame, which we'll assume we are, we can get rid of this q term, because our Lagrangian won't depend on position, right? Similarly, because our frame is inertial, we can also get rid of time. And thirdly, we need to get rid of direction somehow, or we can't get rid of direction. So think about this, this q, right? This q dot is some vector of like x dot, y dot, z dot. And this inherently has some sort of direction. So if we raise it to an even exponent like 2, then it turns into something like this, which is a scalar and doesn't have any direction. So if we make our Lagrangian instead a function of q dot squared, or I should say, I'm going to call it v squared, just to match what Landau does. Now we've gotten rid of dependence on space, dependence on time, and dependence on direction. okay? And this is perfect for a free particle. And I'll note that my choice to raise the power to 2 isn't totally arbitrary. If I were to raise the power to q to the 4th, I could also remove direction, but as we'll see, we're going to have to end up using this total time derivative thing that we talked about. And if I were to use q to the 4th, then I wouldn't be able to do this time derivative thing. Hopefully it'll be a little more obvious when we get into the math. So our Lagrangian is some function of velocity squared. And let's imagine another frame, or another Lagrangian, L prime. And we'll say that this L prime is moving at some velocity v prime squared, or is moving at the velocity v prime. So to imagine this, we'll say that L is in this system here, and L prime, I wonder if I can just change the color here. Yeah, L prime is this frame here. And L prime, or this other system, is moving ever so slightly faster, or the difference in velocity of the two. These both could be moving, but this red one, the prime, is going to be moving a little bit faster. And that difference in velocity is going to be something we call epsilon. Okay, so this epsilon is this tiny difference in velocity between these two frames. Okay, so because both frames are inertial, that means they have the same equations of motion. And that means that we can express this L prime in terms of L, and if we just substitute in v prime squared instead of v squared. Okay? And if we expand this, if we say that, I don't know where to write this, we'll say that v prime is equal to v, say this is v and this is v prime, is equal to v prime, sorry, v prime is equal to v plus epsilon. Okay, and let's make this epsilon green. Okay, so now when we square this, we'll say that v prime squared by FOIL is equal to v squared plus 2 v dot epsilon, oops, I should do green, plus epsilon squared. Okay, now think about what we're doing here, right? We have a Lagrangian of velocity squared, and what we're trying to do is we're trying to find what happens when we add this term to it, when we add 2v epsilon plus epsilon squared. Okay, and if we want to do something like this, we can use the Taylor series. And in case we're not familiar, I'll write it out here. So what this allows us to do is find f at x1 when we only ever know f at x naught. Okay, and I should mention that there are some extra terms here, but I'm only going to worry about this main term because these other ones we can neglect. So in terms of the Lagrangian, we can write this as L prime, which is really just L of v squared plus 2v epsilon plus epsilon squared equal to L at v squared plus L derivative, and we're doing respect to v squared. So actually this is a total derivative because L only depends on v squared. And then we look at the difference between this guy and this guy, which turns out to just be these terms here. So we have 2v epsilon plus epsilon squared. Okay. Now, remember, epsilon is some very small velocity, right? And if you have something very small and we square it, it's negligible. So you can think that as epsilon goes to 0, this term here is going to shrink way faster than this term, right? So we can actually neglect this term, and this will make our calculations a lot simpler. So remember, this whole thing here is supposed to be equal to L prime. And these are two different frames that we're talking about. And in order for these two frames to have the same equations of motion, they have to differ only by a total time derivative, right? And because we've already assumed Galilean relativity, we know that these two have to have the same equations of motion. So in order for these to have the same equations of motion, that means that this bit here has to be some sort of total time derivative. So in order for this to fit the requirement of being a total time derivative, because we already have a velocity term here, that means that everything else has to be a constant. Okay, if we have like some other q term in here, the math won't work out for a total time derivative. Okay, so that means that we already know epsilon and 2 are constants, but this means that this value of partial L, or sorry, dl over dv squared has to also be constant. So this is const. Okay, and this is going to be hand wavy, but from experiment, we find this constant to actually be equal to mass over 2. Seems pretty neat, right? Now, I wish I could explain this better, but I'm not aware of any simple way to explain this. But now if we have this property where dl over dv squared is equal to mass over 2, then if we integrate both sides with respect to dv squared, we'll have L is equal to this integral of m over 2 of dv squared, which equals to 1/2 mv squared plus some constant. Okay, and remember, if we have our Lagrangian here with the principle of least action, and we have some well like this, and then we shift the well upwards by some constant, the equations of motion don't change. So we can totally just ignore this constant here. It has no physical meaning. So we can really say that our Lagrangian L is equal to 1/2 mv squared. And this might look familiar. This is like what we call kinetic energy, right? And we'll see in a bit why that this is kinetic energy. Okay. But let's not forget about L prime, right? We're trying to find how L prime is going to relate to this. So if we know L now, we can pretty much just substitute V with V prime. So we'll say L prime is equal to 1/2 mv prime squared. And as we saw, this is going to expand to 1/2 mv squared plus 2v epsilon. And I'm neglecting the epsilon squared thing again. And this will be 1/2 mv squared plus mv epsilon. Okay, and again, notice that this is a linear function of velocity, and this is constant, this is constant. This is a total time derivative, which means we can neglect it, and L prime is going to have the same equations of motion as L. So this is a very tricky part of classical mechanics, in my opinion. From here afterwards, like deriving Newton's laws and the conservation of energy, it's a lot more intuitive because you can rely on math. Here you have to kind of like go down to the fundamentals of space and time and all that stuff, and it does get tricky. But hopefully this could have helped you a bit. Again, I'm going to have some links in the description to the Physics Stack Exchange that can answer some of these questions. But hope you enjoyed the video. Thanks for watching. Stay tuned for when we get to derive Newton's laws and the conservation of energy, and maybe also the conservation of momentum. I don't know how long I'll take this.